The world of artificial intelligence is evolving at a pace that feels almost surreal. We've moved from simple pattern recognition to systems that can generate entire essays, compose symphonies, and even simulate human-like reasoning. But behind every breakthrough lies a deep, often underappreciated foundation, the architecture of the models themselves. Today, we're diving into one of the most powerful and misunderstood innovations in modern AI, transformer-based models, and specifically, the attention mechanism that powers them. Let's start with a fundamental problem: traditional sequence models like RNNs and LSTMs. They process data one step at a time, words in a sentence, frames in a video, pixels in an image. That sequential processing works, but it comes with a cost: vanishing gradients and slow training, especially for long sequences. If you're trying to understand a 1,000-word document, the model has to carry information through hundreds of steps, and the earlier parts tend to get lost. Enter the transformer, introduced in 2017 by Vaswani et al. In the landmark paper, "Attention is all you need," this architecture flipped the script. Instead of processing sequences step by step, transformers analyze all elements simultaneously, every word in a sentence, every token in a sequence, using a mechanism called self-attention. So what exactly is self-attention? Imagine you're reading a sentence: "The cat sat on the mat which was red." When you get to which was red, your brain instantly connects which back to mat, not cat or sat. You're not reading linearly, you're making intelligent, dynamic connections across the entire sentence. That's exactly what self-attention does. For every word in the input, the model computes a weighted sum of all other words, where the weights represent how much attention one word should pay to another. Let's break it down technically. Each input token, say, cat, is first converted into a vector using an embedding layer. Then three key vectors are derived: query Q, key K, and value V. These aren't arbitrary. They're linear transformations of the original embedding, learned during training. The query represents the current word's question: what am I looking for? The key represents what other words can answer that question: what do I have to offer? The value is the actual information to be retrieved. Now, to compute attention, we calculate the dot product between the query and each key. This gives us a score, how relevant each word is to the current one. We then normalize these scores using a softmax function, turning them into probabilities that sum to 1. This is the attention weights, a distribution that tells the model: for this word, pay 70% attention to mat, 20% to cat, and 10% to sat. Finally, we multiply these weights by the corresponding values and sum them up. The result: a new, context-aware representation of the original word, one that incorporates meaning from the entire sentence. This is the core of the scaled dot product attention mechanism, and it's what allows transformers to capture long-range dependencies with ease. But that's just one component. A full transformer model stacks multiple layers of these attention mechanisms. In the original architecture, there are two main components: the multi-head attention layer and the feed-forward network. Multi-head attention is where things get even more powerful. Instead of computing one attention function, the model runs multiple attention heads in parallel. Each head learns different kinds of relationships. Some might focus on syntax, others on semantics, some on coreference, others on tense. For example, one head might learn that the cat and sat are related in a subject-verb relationship. Another might notice that mat and red are connected through color. By combining these diverse perspectives, the model builds a richer, more nuanced understanding of the input. After the attention layers, the model passes the output through a position-wise feed-forward network, a simple two-layer neural network with array LU activation. This introduces nonlinearity and allows the model to transform the representations further. And because all of this happens in parallel, transformers are massively more efficient than RNNs. Training time drops dramatically, and the model can handle sequences of arbitrary length, no more bottlenecking at 100 words. But here's the real kicker: the transformer's success isn't just about attention. It's about parallelization and scalability. Because every token can be processed independently, the model can leverage massive GPU clusters, enabling the training of models with billions, sometimes trillions, of parameters. That's why we now see models like GPT, BERT, and Llama built entirely on transformer architecture. They're not just bigger, they're fundamentally different in how they understand language. Let's talk about position encoding, a crucial detail often overlooked. Since transformers don't process sequences in order, they have no inherent sense of word position. So to preserve order, the model adds learnable positional embeddings to each token. These are sinusoidal functions that encode the position of each word in the sequence, like a built-in clock ticking through the sentence. This allows the model to distinguish between "the cat sat on the mat" and "the mat sat on the cat," even though the words are the same. Now the full transformer encoder block, used in models like BERT, consists of 1. A multi-head self-attention layer. 2. A residual connection and layer normalization. 3. A feed-forward network. 4. Another residual connection and normalization. And this block is repeated many times, up to 12 or 24 layers in large models, allowing information to flow through deeper representations. On the decoder side, used in models like GPT, the architecture is similar but with a twist: causal masking. This ensures that when predicting the next word, the model can only attend to previous words, not future ones. That's how GPT generates coherent, forward-moving text. So what makes transformers so transformative? It's not just speed or scale. It's flexibility. The same architecture can be adapted for translation, summarization, question answering, code generation, image modeling with vision transformers, and even protein folding AlphaFold. And the implications go beyond language. The attention mechanism has become a universal tool in AI, used in audio, video, robotics, and beyond. But it's not perfect. Transformers are computationally expensive. The quadratic complexity of attention, O(n)(2) in sequence length, means that processing very long documents becomes prohibitive. That's why researchers are exploring alternatives: sparse attention, memory-efficient attention, and hybrid architectures. Still, the transformer remains the gold standard. It's not just a model, it's a paradigm shift. It taught us that context is everything, and that the way we compute relationships between data points is just as important as the data itself. So the next time you ask an AI to write an email, summarize a paper, or explain quantum mechanics, remember, behind that response is a network of attention heads, dynamically weighing every word against every other, learning not just what words mean, but how they relate. That's the power of the transformer. That's the future of AI.